want to comment that here the wire, even it's a non-ideal conductor, so it what means that you cannot treat it as a equal potential surface. So remember that here there is the voltage 0 and the voltage V. So if it's a superconducting surface, or if it's a perfect conductor, then you cannot have a voltage difference between the two ends. So say that if you apply a voltage on the right hand side, then the current flowing in the superconducting surface will have infinite current. So that violates the property of the superconductor. And the second thing is here in this example, here there is a capacitor on the left, and you have a resistor on the right, and now you can see that here initially before the switches on, the capacitor stores the energy within the capacitor, right? So it's some sort of energy stored within the capacitor here. And after you turn on the switch, what it does is that there will be current flowing through the circuit, and then there will also be the voltage difference between the two ends, and there will be electrostatic fields built up along the circuits. And you can sort of imagine that the electrostatic force is responsible for delivering the energy on the left-hand side circuits to the right-hand side resistor. So in the end, all the heat is being dissipated at the right-hand side. And so if you calculate the I squared times R, which is the power, and integrate it and from 0 to infinity, I think what you would get is the energy stored inside of this capacitor, so which will give you the electrostatic and total electrostatic energy. So here, the source term exists only in the battery on the left-hand side, and on the right-hand side there is no source term, so the Fs is non-zero only at the battery, and the electric field here exists both in the battery and in the resistor. In the battery, the electric field is negative along the current direction, but on the other parts it's positive along the current direction. Okay, so let's try to get a few more examples. So now consider the case that there is a parallel plate capacitor, and we apply a loop. Some portion of the loop is within this parallel plate capacitor. So you imagine that along the wire here, so it's not completed. So here you imagine that the EDL will be positive when the circuit is inside this capacitor, because if there is a voltage difference between the two capacitors, then the electric field within this region should be finite, right? And now say that if we attach circuits that's very far away from this capacitor, where the field here, say, is almost exactly 0, so then there won't be any current flowing on, there won't be any electric field along this resistor, right? But will there be any EMF built up in this loop? So now, if you assume that this is an ideal parallel plate capacitor, then there won't be any EDL on these two sides, right? So it seems that the only contribution to this EDL, which gives you the curly E, which is the EMF, seem to be non-zero because it's always plus sign along this loop. But this seems to be against the physics intuition. So say that if this is true, then won't it mean that there will always be a voltage difference between this resistor? So there will always be somehow a current flowing in this resistor, and there will be infinitely heating on this resistor, right? So do you know what went wrong? And what should be the why like this somehow the integration of this EDL equals to 0? Because in electrostatic case, the EDL should be exactly equals to 0 because the delta cross E is equals to 0, right? So that's guaranteed. But how can you see that the EDL is 0 in this case? And how can we explain that there is no EMF built up in this loop? So anyone want to have a guess? So on the two ends, there shouldn't be any voltage difference, because if there's some voltage difference, then it violates the like it will provide infinite power to this circuit, right? So, but you see that this loop does not touch this parallel plate capacitor, so this the charge here on the two parallel plate will never dissipate. Right? It only provides the electric field. So this violates the energy conservation, right? So what went wrong in this calculation? Okay, so I'll try to give you a hint. So remember the problem in the midterm that we consider cylinder capacitor, and the oil can rise uh, in between the two capacitors, even though here it seems that the electric field, sorry, it seems that the electric field is always to the horizontal direction and no vertical direction, but it can still drag the oil up. So it's actually the same here. So technically speaking, this E is only pointing upwards in the middle. So because it's not an ideal capacitor, right? So when it goes slightly out, the E field will look like a circle like this. So what it means that now if you look at the current accumulating, or if you look at the E field accumulating on the loop length here, it's providing a integration along the direction over here, and then there is a integration over the EDL on the other side. So this is actually contributed by the fringe field. So even though the majority is along the direction here, this is long enough, and somehow magically the contribution of the fringe field from these two combined together must exactly cancel out the electric must exactly cancel out the contribution that the EDL you get over here. So because this is a static problem, then we are guaranteed that the EDL is 0 for because there is no power or no source contributing to this problem. Okay, so before we move on, I would also want to emphasize that now look, if we go back to look at the first exercise, the wire actually is doing something quite magical here. So now if say that in the case where there's no wire, then if you apply a voltage difference between the two ends, what you get is only in the inside is the E field almost perpendicular to the surface, but somehow once you get to the outside, then the E field will be having a strange shape, right? But once you put the wire there, because the charge, because the current cannot flow out of the wire, then all the electric field should exactly follow this wire, and there won't be any leaking of this electric field. So that's the beauty of the wire, and so even if you bend the wire, the electric field will not leak out of the wire, and what it does is that somehow if you bend the loop, there will be an automatically charge distribution built up along the wire, and say that this electric field so there will be some electric field built up across this wire, and now this field actually help you to guide the current. So the charge will then the charge will automatically follow this path of the wire. So what the wire does is actually something non-trivial here, and this the speed of how the electric field will build up depends on the speed of the light. So that is how fast the information passes. So remember that we consider three speed limit. So the slowest is the drift speed, that is the speed of the provided by the current. Another is the speed of the thermal speed. The fastest speed is the speed of light, which tells you how fast a circuit should be switched on. So say that if you have an extremely long circuit, you cannot simply switch the circuit and touch the circuit and assuming you won't be electrocuted, because somehow the information of you turn on a switch propagates at the speed of light. So even though the drift velocity is extremely slow, the time that you get electrocuted if you touch the circuit will be the speed of light. So never try to touch a socket in your house. Okay, next we will discuss the uh, motional EMF. So now in the previous sessions we talked about the EMF built up by say a battery, but we can also have other sources of EMF. So say that if you have a if you have photons shooting um, on trees or shooting on some diodes, it can also produce a voltage difference. So these are alternative means of creating a voltage difference instead of a simple chemical battery. So this time I want to say that the a motion of the circuit within a electric field or within a portion uh, of electric field that's covered by sorry within a portion of the circuits covered by a magnetic field can also produce EMF. So I guess you are familiar with the content here, right? So in the end, I'll just give you a brief idea about the conclusion first. So in the end, because here you are moving the current to the right, the current here has a loop that if you can define a magnetic flux through the surface here, and as long as there is a surface, there's a change of the flux, and then there will be some motional EMF, and this can also be generalized to other types of EMFs. But the key idea is the change of flux. So that's pretty much summarizes Faraday's law. But let's try to, if some of you forget how this works, we can try to go a bit into details of how the EMF is being built up. So in this example, the EMF is by the motion of the circuits here. So say that if we move the circuit to the right, then a charge here within the magnetic field can feel magnetic force by this V cross B. So the V cross B should be along the direction of the so the charge is already moving some speed, a small speed, say along the direction here, but it's being also dragged. So the total velocity will be somewhere that's not perpendicular to both of this. Then you will have a final magnetic force that's pointing along the direction that's say that it's also not perpendicular exactly to AB or AD, but this will eventually move the charge along this loop. So if you integrate exactly this EMF or exactly integrates the force, the the F over Q, the force over unit charge, you will obtain the EMF. That's if you work this out, you will get is equals to the dl cross V times B. And now this V cross dl equals to, let me see. So the v it should be a little v here. Sorry. Um, so it should be equal to velocity times the b, and also the height of this circuit. So the EMF across this loop is VBH, and now we can define the flux within this loop, which is the B times the area here. Then the loop is the flux is should be the BH times the x here. So the change of the flux equals to the BH times dx dt, which is BH times minus the velocity. Now if we combine the equation here and the equation over here, we can see that the EMF equals to the negative of change of the flux dt. So, but I want to remind you that the magnetic force actually didn't do any work in this process. So that's because if you remember that we talked about this in the lecture 12 of the page 7, you can go back. So here, when the charge moves, the magnetic field is always perpendicular to the motion of the velocity. But somehow, because you are pulling this wire, the magnetic field is responsible to transform your work to the current in this wire. So in this process, if you calculate the force for a charge along this loop, what you have for the integration is a slightly changed shape of, and it's not, you are not getting the charge is not returning to its original place, and if you perform an integration of the magnetic force over this path, the magnetic force actually didn't do any work, and it's the force that you are pulling that did all this work. And now if you calculate the EMF, to calculate the EMF, what you do is not follow the charge across this journey, but instead you are calculating the EMF within an instant moment. So at that moment, what you get is a rectangular loop. And if you do calculate the EMF build up at that instant, the V you can see that the magnetic force along this loop give you finite contribution to the EMF, and on the contrary, because the force, pulling force done by you is always perpendicular to this current here, so it actually didn't contribute anything to the EMF. So the EMF is here is contributed by the magnetic field alone, and so try to convince you that the work done by the magnetic field is zero, but somehow the magnetic field is responsible for this EMF. Now the conclusion, as I just said earlier, that we are not only limited to the simple case where this motion of the current produce a change of flux. We can also have any arbitrary shape of the circuits, and even the circuit shape can change as time goes on. And as long as there's a change of flux, then we can use the change of flux to relate that to the EMF. So now to derive that, we can consider the change of the flux or the change of the surface here. So the surface here is an initial, say it's an initial current loop, and at the next moment we change the surface to the one on the bottom. So there is a change of this shape of the surface. Now remember that we need to use a vector area to represent the surface loop, and for a vector area, any closed vector area is the vector area over any closed surface is exactly 0, because if you consider a vector, then area pointing up exactly cancels the area pointing down. So here, if you integrate the entire surface, enclosing the both the top and the bottom and the edge, then that gives you exactly 0. So now, if you want to get the area difference between the top surface and the bottom surface, what you get is simply the area around the edge. So only this area around the edge will be related to the change of the flux. So now, if you what we can do is to simply to calculate the area of the ribbon, because we now know that the change of the flux will be exactly accounted by the change of the flux across this ribbon. Now to get the vector area of this ribbon, we can sum them up by infinitesimal small area elements, and here by definition say that the initial point at the P goes to P prime after dt, then the P prime difference is V times dt. And we also need to integrate along this ribbon, so there is a dl. So the V times dt cross the dl gives you the direction of the area, and so that is you can also express as V cross dl times dt, and that is the area. And now you multiply this area by this BdA, this gives you the flux. So we can rearrange the terms a little bit, because here this is BV cross dl, but what we are familiar with is the V cross B. So the V cross B is the F magnetic per unit charge. So now that will be the F, the little f, right? So now if here you can transform that to negative of V cross B times dl, which gives you negative of FTL, which this the on the right hand side is simply the negative of the EMF. So that this proves that indeed for any strange shape of wire, and as long as we move the wire to a different location, and there is a change of the flux, then this change of flux will induce EMF, and the EMF can induce a current flowing in the loop. Okay, so any questions? Now, for example, we just realized that to calculate the EMF, we don't need to worry about the exact mechanism causing by the magnetic field. We can simply calculate the change of the flux. So say that, for example, in this case, we are no longer moving the entire circuit, but instead here we only move one segment of this current loop. So here only this black rod is movable, and we put that inside a magnetic field. So now imagine that if this rod is moving to the right, then this will change the flux here. So it will induce EMF. So the induced EMF is simply the change of flux dt, which is B times the change of area. So it's the BL times dx dt, which is BL times V. And now because there is a change of the there is a EMF, and then because there is a resistor here, you can relate the EMF to a current, and remember that the EMF is the potential difference, right? So that is similar to the V. So then the current will be the EMF over the R. Now there is a subtle issue that here this area is a vector area, and so you should assign a sign to this flux, right? So so whether the current flows in this direction or the other direction may not be intuitive if we apply the formula here, because here everything is scalar. So the direction of the current flow is actually hidden in this formula. And if you remember that from physics 2041, what we are supposed to do is to use Lenz's law to determine the flow of the current direction. So what the Lenz's law says that the induced current should always reduce the amount of the change of the flux. We will talk about this later, but use the Lenz's law, or if you want, you can simply strictly following the derivations of this change of flux. You can always figure out the direction of the current flow, but let's skip it for the moment. And now, and assume that it will go simply counterclockwise here. And now, because of this, here this EMF is induced by the magnetic force. So we can also calculate the magnetic force along this loop, which is from the derivation before. We can also see that it's the same, that it's I times dl cross B. in the end you will get the results over here, but again the direction of this magnetic force will be towards the left. So that's because the induced magnetic field is trying to slow down the change of the EMF. So say that you can sort of imagine the force produced by the magnetic field sort of like a friction. So it will always be against the direction of the change. So say that if you want to move the rod to the right, then the 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 EMF will produce a current such that it will reduce the change. So it will try to pull the rod backwards. And that's in the Lenz's law. So now what we can do is to calculate what happens if the bar start out at velocity v0, and then because of the within the magnetic field will always give a force against the motion, so it will always slow the rod down. So now you can apply the Newton's second law using the F equals ma, and you can derive that the ma here on the right can be related to the magnetic force here we just calculated, and this gives you an ordinary differential equation here, because on the left hand side there is a v, on the right hand side there is a v dot. So again, from this expression we know that the solution must be an exponentially decaying function. So here what it means that the velocity here will exponentially slowing down if you give it an initial velocity, and it will slow down exponentially. So what this means in terms of energy? So now if we calculate the power or if we calculate the energy dissipated by the resistor, then that's simply I squared times R. So the amount of the heating in unit time is also an exponential function, because the voltage is an exponential function, and so the current is also an exponentially decaying function. So now if we do an integration over the power dt, then that gives you the total dissipated energy. So if you do this carefully, what you arrive, you must get the total initial energy back. So the total kinetic motion of this rod is 1/2 mv squared. So what you get in the end should be also exactly 1/2 mv squared. Okay, so in the next lecture we will discuss the electromagnetic induction. So what I mean is that in the lecture today, what we discuss is the EMF induced by the magnetic field, because we are moving the circuits here, and the movement of the charge inside of the circuit can be changed by the magnetic field, and if we move the circuits here, we already know that there can be a magnetic force here, and this magnetic force can drag the charge and produce a current. So this is one type of movement, and you can sort of imagine that this is the EMF induced by the magnetic field. But we also have different types of change in flux. So, for example, say that here we are we are making the current loop staying still, but instead of moving the loop of this circuit, we move the magnetic field. So if we move the magnetic field towards the left, then there shouldn't be any magnetic force at all, because here the magnetic field is exactly the same here, and it doesn't contribute anything to this EMF. So the EMF here this time shouldn't be magnetic field related, but somehow because of the special relativity, so moving the current towards the right is actually identical of moving the moving the field towards the left, because say that we can at the left hand side observe the current loop by observer that's staying still with staying relatively zero motion with the current loop. On the right hand side, we can still do the same, and what we observe should be the identical physical results. So we should expect some change of this EMF and also the change of induced current. But this current, the physical origin of this current is no longer magnetic field. And what we can do in the third type of experiment is, even when we keep the two holding still, and only change the magnetic field strength, this will also change the flux, and expect that there is a induced current, and so this case for the magnetic field is very different from the case by a different mechanism, but their total result can also still be explained by the same expression. So this is actually what Faraday did the three sets of experiments, and from these three sets of experiments, he summarized Faraday's law. That is, no matter what kind of mechanism that causes the EMF, the change of the flux dt is always related to the EMF. So just try to give you a brief overview of what we are going to discuss next on Thursday. So what we are going to do is to get more familiar with the Faraday's law in the Maxwell's equation. So here we can, if we assume this is correct, then we can derive the differential equations of the Maxwell's equation, one of the Maxwell's equation, very easily. So now here we can rewrite the left-hand side, the total EMF, by the loop integral of E dot dl, and on the right-hand side, the flux is the B dot dA. So if we write this out explicitly, the what we get on the right-hand side is partial B partial T dA, and now this is the already the Faraday's law. However, this is an integral form of the Faraday's law. We can convert that to the differential form if we use the Stokes theorem. So I don't know if you still remember that the Stokes theorem can relate a closed loop integral into a two-dimensional surface integral. So this is one of the fundamental theorems of the differential in high dimensions, and now on the right hand side, it's also a two-dimensional integral because it's an integral over dA, and because this loop is applies to any surface, so that's that's guaranteed that you have to have what's inside identical to this one inside as well. So that's how we get the differential forms of the Faraday's law. So that's del cross E equals minus partial B partial T. So in the electrostatic case, then this directly gives us the del cross E equals 0. But remember that this is only a static case. So next week we will discuss this electromagnetic induction in details. And if you are not familiar, please remember to review the chapter 12. And they will include a lot of the fundamentals about the electromagnetic inductions.